Let them choose what they want to work on. You need very resistant.
I don't think I can.
He read it and then
I don't think.
the plan is for half an hour, let's do some exercises. So I think there was a email sent to everyone. So there's a link for exercises. There are, so the exercises are labeled as GGT1, GGT2. So there are some exercises for the first part. And then if you skip a few pages, there are a couple of exercises on the CAT 0 geometry. So the plan is, you can turn your chairs around and work with people if you want, like discuss freely with people. We'll not do anything on the board. Aishwarya is here, I'm here. If you have questions, you can ask us. Okay. Yeah, you can make partners or groups or whatever however you want to do it. And then if you have a question, you can ask one of us to come and we can help you. Okay. Yeah. Any questions besides the ones that are on the
Here we might need you. Yes.
Yeah, the idea is to get you to think, so you can choose what question you want to work on. Like I said, I'm not going to, neither Aishwarya nor me will solve anything on the board.
It's the sheet named Geometry of Coxeter Group Stack.
Yes.
Yes.
So now it's just to go to the base character. Exactly. Oh, yeah.
After release on that.
No.
हाँ सबसे मतलब ये बहुत diameter at that stone.
Yes, first one is that.
Second.
I would say. Having to define on URL genetics factor. Just as an output.
His homes. Oh. Oh, sorry. Was on YouTube. Identity of things. One person total.
Yes. I haven't spoken. Maybe you like to talk. You can talk to your friends. Minutes.
I really scared the
Word length is infinitely long. Telegraph.
Shows us to be useful in the
Different players.
Cell complex, you remember cell complex? So basically, if you have made out of cells, by gluing some cells together. I think that's sort of. So complex means, so you can do remember simulation complex? Yeah, so pretend it's a simulation complex. Yeah, this is complex association. TW is like a generalization of that. But solve this for simplicity.
Why? Oh, that's a
Two compartments of this, and. This F1 and 2 condition goes also, this word.
Check Google Docs, each Google. Accelerated. Thank you.
Because we make spaces to it's always well. The upper part has so suppose you see some B trigger as two and I so there you can so we finally fix this.
The questions if you want to look at. Did you want to look at the questions? It was just sent by emails, but I can, yeah, but I can.
X, Y was, isn't it? That would be good. Good to know.
I don't know all of them. All of them. I included.
We have to finally figure out this could change on your and so for the compound.
That is. So if you me
You don't want to come
but one thing is, you're talking to the left hand side of and not the other way around. So this is like for one side. If there is a map there.
70 years.
Now X to Y and get this bound. Now to get this other bound, you have to basically.
The word position. So.
So this is your section. Then it is back section. Then you get the whole file. That's what I'm trying to look at here. This side is this.
For example,
It's not a B, it's a situation.
This
Just not your contract. I give you the equal. But the other side.
But it is not, this have. Yeah, yeah, this not like.
Now this.
Because we have this because.
Then this not plus.
So looking is this.
And that's actually equal. Yours is N1 and one, then another N1.
So basically, let's get
What is
even minus of frequency or non-empty. Oh, how many lectures?
Action is like, this is going here.
Right.
It's only one.
One, yeah. Then they become loops.
Yeah.
Yeah.
And so now it's a
sort of, yeah.
Yeah.
Like you think of coverage. Can you draw a cover of this? To be healthy.
All good.
So.
What do I? From
Yeah. Only thing that I will manage is.
Yeah.
Yeah.
Now I got it.
This is not good, this is not here.
A, B, C are all, then whatever we, one, they might be positive or negative. L1 may be negative. In that case, when it's going here, it's actually decreasing L2 minus L1. But here,
Because of the.
counting L1 plus
They
L2.
do actually, so they can-
This is the distance. So it's not isometric. This is the. For the domain.
And then the
And also, the domain is.
Yeah, that's not something but ends. Ends, ENDS.
Whatever you're doing, you want to.
So it is cause for.
What is this?
Okay, then.
F2
What lines? I want that. I will take it up.
and there is my answer, so that we just. So what?
Just telegraph function pages. What is required for someone to Enter bar find it. Because.
Heuristic assessment. The isomer with the point.
Maybe in 5 minutes, we'll start continue talking about Casio. Candy spaces.
So here you can actually take.
Yes, that type somebody. It's not obvious to me why we actually spoke about. Proper thing is not coming. So really discontinuous the thing. Yeah, it was. Spoke about. It's like it's something. Yes. Yeah, otherwise, yeah. Yes.
Why not like lunch first? When I
So you're saying you won't cancel out? He's coming to the left, and he's coming to the right. So that's not fine.
8 is X and XK. If I distribute the sales in XK, so then that is fine, then I'm taking the finite.
That show that it's here the proper, corporate action of it.
GK is the full. That trees.
Yeah. Then from extra. Because I was directly.
Yeah, that is also figure eight.
That's not really said here,
Yeah.
up to
Up
this
to
here,
this figure.
it is here.
This one we have to move.
We get a bomb.
I think Vilna Shores is the easy. Yeah,
Develop the action and
right,
F3 on the website on KEW.
yes.
You just map the third generator to one of those ARP or
But you need the action to be proper and proper. So if you randomly
do that.
do something, then it might not stay proper. Um,
Whether it becomes always or not always, what's like? What's it? And then it's was there. I think it's not.
You just have a subjective good officer.
But
No. Always have a subjective marker triggers. Right. That was G1 cross G2. It must be one. And then
So in this F2 and F3, probably we go to the name of there probably won't be a QI homomorphism, right? Group homomorphism. Which is.
There will be.
You can map the third generator to one of those ARP.
So I think you're thinking of it the opposite way. Think of F3 as a subgroup of F2,
But then the.
not as like,
F2 as a subgroup.
yeah. Think of F3 as a subgroup of F2.
But then the post subjective it will be become about.
F3 is a subgroup of F2.
You take a.
Think of any FN as a subgroup of F2.
Okay.
Then you can try to use Miller Schwartz again. Okay, should we wrap up the exercise? Yes, probably not enough time to, I also wrote down a lot of exercises. So you can think about them. And I don't want to solve them on the board because I want you to ask why you got stuck at something and not just tell you the solution. So feel free to ask Aishwarya and me anytime to do tomorrow if you have more. Yes, sorry, I'm not solving anything on the board. But if it really bugs you that you don't know the answer, then either you'll find it or you'll ask. Okay. Now. So let's continue. Let's continue with cat zero geometry. So I do want to clarify, I think Aradhana was asking me this question, right? So let me write the definition again of cat zero. Sorry, I keep saying cat zero. The general definition is cat k, but I mostly think about cat zero. That's why I keep saying cat zero. But cat one is important for us as well. The reminder, it is in metric space. X is cat E space. Okay. For every geometric triangle. Of perimeter less than 2 dk, where we call dk was infinite if k was less than equals to 0 and dk was pi by square root k if k was. So this condition is only needed when you have positive curvature. Otherwise, if you're looking at non-positive curvature, then you don't need this perimeter condition. You really think about every geometric triangle. But if you're thinking of positive curvature, then you're only concerned with these bounded diameter triangles and corresponding comparison triangle. Time in this model space. The following is true. This triangle in X and this triangle in M3A. It's what's B1 into B3, B in time, into prime, B time, B1, B3. B1, B3, and then if you take 2 points P and Q, and then you take 2 points P prime and Q prime here with the same distance from B1, then the distance between then the distance in X between P and Q has to be less than the distance in the model space between P prime and Q. So if this happens, then the space is called cat K space. Okay, so let's do this quick exercise together. Show that our tree is cat K for all K. Yeah, maybe just take 2 minutes and think about how you apply this definition to a tree. So, yeah, pick any tree, infinite, non-infinite. Maybe pick the 3 regular tree. So just try to apply the definition to this tree.
So the triangles will be just the trivial.
In the tree?
In the tree.
Yeah, in the tree, every triangle is degenerate. If I take any 3 points, what's the geodesic triangle joining them? So this is one geodesic. Yeah. Maybe I should, let me just take the tripod. Let's see if we can just do it by definition. Not sure if you can. Yeah, I should, yeah, let's see, if I try to apply the definition. Yeah, let's try to apply the definition and see if we can actually prove it using the definition or not. So I have B1, B2, B3. So, okay, let's do cat 0 for now. Okay, let's just stick to Euclidean. So in Euclidean plane, I want a triangle with these same edge lengths. So let's say these are all one. Let's say these are all one. So I'm looking at a Euclidean triangle of edge lengths 2. Sorry, equilateral triangle. Right? And so now if I pick a point P here, so now I have to be careful. Let's say I pick P1 and P2. But what do I mean by P? Let's say P2 and P3. By that I mean P2 is on the side, the V1, V2 side. So I have P2 here and P3 here. Okay, it's the same point here, but on the two sides it's 2 different points, and these are the same distances. So clearly the distance between P2, P3, which is the same point here, that's 0, and that's less than this thing.
But P1 and P2 are elements of that metric, because if the exist points of that metric space are just this vertices of the graph, right?
No, I'm thinking of the tree as the matrix, the whole tree as the
So
matrix.
if you look at it like geometry,
Yeah. And P2, P3 are points on the sides of that triangle, but here the triangle is degenerate, that's why I chose this thing. Yeah.
And the P and Q has to be same or no?
No, this is just one case that I,
Yeah.
the one case that I, in fact, I'm about to tell you that it's hard to do this by definition. Because for these points, for points here, which are on E1 and E2 and E3, it's easy to see that there's a 0 here and that's not 0 here. This satisfies the inequality. But if I take P here and Q here, so then in my picture I have some P prime here and some Q prime here, and now I have to compare this distance. So we have to compare this distance to this, this distance. That's the distance between PQ. Yeah, so now it's not so clear to me.
maybe we go more product.
No, I don't really need that. But I think, yeah. I think I need a theorem to do this. But does everyone understand how I'm applying the definition? Like if I just want to apply the definition, then what do I have to check? I have to check like for any 2 points PQ on these two sides. I look at where they lie here, P prime, Q prime. So this PQ, if I chose PQ on this edge, if they are actually the same point on this little piece, then it's obvious. But PQ could be here, and then it's less obvious. That's all I'm trying to say. Okay, so what's the theorem that I want to use? So okay, first the definition. Space has curvature at most k. This is the or this is equivalently called or it's locally cat k if every point has a neighborhood which is cat. Every one has a neighborhood. So cat k neighborhood. And then the theorem is a complete geodesic metric space. Of curvature at most k. Is cap k. It can only if it has no isometrically values of length less than is. Is so in particular, if k is less than or equal to 0, I'm asking that it is simply connected. Right, because if k is less than or equal to 0, so this, I mean, this is a not to say the proof, but if I know if the space is locally cat k, meaning neighborhood of each point I know it's cat k, then how do I say that the whole thing is cat k? Because for the whole thing, I need to check things for every geodesic triangle. Yeah. And I have to only check that it doesn't have isometrically valued circles. Of length less than 2 dk. So for example, if I take the torus, so take the square and identify the opposite sides. Right? I claim it is locally cat 0. So locally cat 0. But if it's okay, well, I should say what's the metric on this? The flat metric. I'm not really thinking of it as sitting in R3, but I'm really thinking of it with the metric coming from that square, the flat metric.
So this, in the theorem, this hypothesis in which side? Your top one, this k less than or equal to 0, it is simply connected.
No, in particular,
Okay.
yeah, I was just
It's a
saying.
corollary of this. No.
No, I was just I was just saying if, what does this second sentence mean if k is less than or equal to 0? I was just saying, the second sentence is saying that the space is simply empty.
Okay. So there is infinity.
Yeah, exactly. So I'm saying there are no isometrically embedded circles. Yeah, so this torus with the flat metric, that's locally cat 0, is clearly near every point I have the Euclidean, looks like a Euclidean space. But it's not, it's not simply connected. So it's not a cat 0 space. It itself is not a cat 0 space, but its universal cover is a cat 0 space. Is a cat 0 space. Right, its universal cover is just R2. A Euclidean plane. So that space is cat 0. And the theorem here is this Carta and Hadamard theorem. Which again, I think Carta and Hadamard, they proved it for non-positively curved Riemannian manifolds. It's coming from manifolds, but the theorem is that if you have a locally cat, just say cat 0. If you have a locally cat k, if you have a locally cat k space, then its universal cover is cat k.
So excuse me, can you please tell me what the flat metric here is?
By flat metric, I mean,
So the points here are just the vertices or actually?
No, I mean, sorry.
Okay, yeah, right.
Yeah,
So if you take a point on one side and the other point on the other side. Okay, so what would be this?
Like if I take
Point
this
there,
point
yeah,
and this
yeah.
point,
It's
anyway,
the length of that, is it?
I won't take.
But it also depends upon, just how this. Like this way, right? Because, I mean, you're writing it, So if you take a right angle triangle, if you take a square, that distance will be something.
Hmm.
But if like this,
It's a parallelogram, then.
Yeah.
Yeah.
so. Yeah.
Just
Yeah, I guess take any one, but just fix one. Even if it's a parallelogram, it still has the Euclidean, local Euclidean structure.
So flat metric means the Riemannian metric coming from R3 on the torus, right?
R2, not R3.
No.
I'm not imagining it sitting in R3.
Oh, okay.
Yeah.
You're just taking inside R2, just with this
It's
identification.
not inside R2.
Like
Ah.
with this identification.
Yes.
Oh.
Yeah, I'm thinking of it as an intrinsic metric, not, because when it sits inside R3, it has curvature.
Yeah.
I'm claiming it's locally cat zero. It's not, yeah. It's the intrinsic curvature here.
This has curvature through local. That's right.
Locally it's curvature zero. Yes. Okay. Let's do, I'll tell you a black box, and then using that black box, let's prove something. So, remember the whole point was, like, if I was.
Sorry.
Yes.
So this would be like Riemannian manifolds with boundaries. There concept comes this thing, or
The.
in this when you're trying to define the metric, will that because the boundaries.
This doesn't have a boundary.
In this figure, before the identification, like that's my question. I'm confused about that. Like when you say you're taking the Riemannian metric from R2.
It's like, so if you have a cylinder, if you have this paper, it has the metric from R2.
Right.
And even if I make it a cylinder, I can
Yeah.
still have the locally flat metric on the cylinder, right? And basically, I'm thinking it has that same metric. And when I do the torus, I'm thinking it's a flat metric. Yeah, no, sorry, I'm not giving a satisfactory answer.
Okay, so
Metric locally defined.
Yeah,
I think I'm more confused with the technical part, whether their boundary has to be concerned or like when you take the open charts, whether you have to take the charts at the boundaries where on half planes and all will come.
I mean, like if.
Yeah,
the point
those
of the
places,
chart
yeah.
is-
These things, right?
This would be it. Okay, so let's do yeah, basically now I want to tell you what do I get if a group acts on a, so okay, maybe let me give you a list, a quick list. The consequences, and then we prove one of them just to, so that you can really see it. Consequences of acting on a cat zero space. So yeah, now I really mean cat zero here. Because recall our goal was to prove that every Coxeter group acts geometrically on a cat zero space. So what do I get if I know such a thing? So if I have a thing geometrically on a cat zero space, so I get a lot of things. So what I get is G is finitely presented. Okay, I get G has finitely many conjugacy classes of finite subgroups. Yeah. This one I want to show you the proof so that you can see something in action. Maybe let me not write it. One more thing that you can get is all solvable subgroups of G are virtually abelian. You don't have any crazy solvable subgroups. They're all virtually abelian. And you get that every abelian subgroup is finitely generated for such a G. You can prove the word problem for such a G. What's the word problem? You have somebody gives you a presentation of the group, and then somebody gives you a word from that using those generators. And I ask you, is this word trivial or not? Did I just like make a word of length 100, but secretly it just all cancels out? Like, can you come up with an algorithm to figure this out? In general, you can't. For arbitrary group, you can't, but for these cap-zero groups, you can. Conjugacy problem also you can solve. So yeah, these are, so yeah, just wanted to say these are some of the things you can get by if your group is acting geometrically in a cap-zero space. Basically, I know all these things for Coxeter groups then. So if you want to know what are the solvable subgroups of Coxeter groups, they're all just virtually abelian. Virtually means they have a finite index subgroup, which is abelian. So let's just let's quickly see number 2 in action, just so that
Geometric action means what?
geometric action means acting properly, discontinuously, and co-compactly. And then nonlinear what? It's quasi-asymmetric. So the group is quasi-asymmetric. So the space is really capturing something enough about the group. So I want to prove. I call it a proof sketch because there's a big black box that I want to use. So the fact I want to use is every bounded set in a cap-zero space has a center. Okay. Maybe you can think at least in Euclidean plane that's true. If I give you some bounded set, you can find the center. You take a ball around that center point to contain that set. But if I give you finitely many points in R2 or in Euclidean plane, you can find the center for those finitely many points. So using this, let's see how will I prove that there are finitely many non-DC classes of finite subgroups? Okay. Okay, so I have my group acting. So G is acting on X, which is cap-zero, right? So it's acting geometrically. So what does geometrically mean? I have a co-compact action. So co-compact means I have a compact set K such that G dot K is X, right? And what does proper mean? Properly discontinuously. What does it mean to act properly discontinuously? That is, in particular for this compact set, the number of elements that don't take K off of itself is finite. So basically I can say there exists a finite set F in G that fixes a point in K. That really use both, that the action is co-compact and that the action is properly discontinuous.
Why would the last statement follow? Both your hypothesis on the action?
Because, so properly
Yeah.
discontinuous means
Yeah,
the number of elements that
yeah. Right.
don't take K off of itself is finite.
Hmm.
So in particular, the number of elements that don't take a point off of itself in K
Okay.
is going to be finite.
Can you repeat once that definition center? The notion of center in the fact you wrote every bounded set in a cap-zero has center.
Center is like in Euclidean space, like I'm thinking of, if I give you some finite number of points, I can find a center, meaning it's equidistant from all those points. So at least for finitely many points. And then if it was a bounded set, then the center would be like, it would be a point. So say if I take a ball of certain radius, then the whole bounded set. I think it would be the optimal ball, which would contain that set, something like that.
Okay.
But you should, yeah, what I will use is just for finitely many points. It's now if H is a finite subgroup of G. Then we orbit any point Hx with the bounded set for any x and g, right? H is a finite group, so I apply to a point, I get finitely many points, and I can put them in a bounded set. So then there exists a center, then I'm using my fact. X naught. That is fixed by D. Because what's the picture? I have these finitely many points. Oops. H1x, H2. Right? H5x. And I have this center point which is equidistant from all of them. So if these points are preserved by H, the center point has to be fixed by H. Okay, now there exists a G, now Gx naught is in K for some G. I'm just moving, I just want to move this picture. I had my K, I had my K here, so I just want to apply G to just bring it into K. Therefore, GH, G bar, a conjugate of H fixes Gx naught, which is contained in K. And hence, GH, G bar has to be contained in this finite set. I think that's good. So what did I do? I brought my finite subgroup. I brought its conjugate into my finite set.
How the third line follows.
There exists a center. That I'm using this fact. That is because of this picture. I have these finitely many points that are invariant under H. And the center is, in this case, the center is a point which is equidistant from all of them. And it's a unique, maybe I should also, has a unique center, I should say. Now, so there's a unique point x naught like this. So if I apply H to this point, any H to H, then it has to fix the center.
Action is like isometries.
Action is by isometries, yes. Yeah, my definition of geometric also was included isometries, thank you.
So the uniqueness of not there, then
Right. Actually, maybe like you were asking, I think I need to possibly justify this more. Because I'm saying like this F is,
So you're like giving this Euclidean example, EN, you're only talking about E2 or E3 also, sir?
E3 is also okay.
No, so then if they have just a finite set of points, then there is excess 1 point above and 1 point below, which are equidistant from each one of them. I just take a finite number of points in the circle and plane. And you don't just,
Or like the whole line
Whole
just
line.
passes through the center.
but I think perhaps we could like this you should throw in some more words in terms of hypothesis.
Right, yeah, that's a good point.
But it can't fix a whole line because it can fix only finite.
No, like I think this objection is I said there is a unique center which is equidistant from these points, but that's not true in like in R3, like if this is my plane and I have these points,
Yes,
the whole line is equidistant from every point on the line is equidistant from this guy. And maybe I should really be saying something about the ball of radius R. There should be something about a ball around that center point containing
then you will
all the
have two,
points. Huh?
then you'll have two such points, right?
Then why will I have?
No, it just got. In all three, if you have just have access to some finite number of points, at the circular distance or, then you look at the global radius or over. But the intersect will find 2 points. Right?
This is North Pole and the South Pole still.
Yes. So if like this, modify or whatever.
Yeah.
No, but I think
Okay.
I'm thinking, what is the difference between a cat minus one space and a cat minus 100 space?
Not much, just,
Toilet?
I mean, not
I
much
don't
in the sense, like the model space, like forget about the cat part, but the model space with curvature, constant curvature -100 and the model space with constant curvature -1, there's like, this one's a scale version of the other.
Is a matter of scale.
Yeah, it's just a matter of scale.
I think that's one of the fundamental theorems, right? That
Yeah.
like this whole. You request isometric correction. One
One of those three. Yeah, so actually like, I mean, I'm sometimes talking about cat K, but all I really care about is whether that K is 1, 0 or -1.
Yeah.
That's essentially all that matters.
Yeah.
Yes, I think I'll look up the center business.
Yes.
I agree, there's something missing.
This is like this is a tutorial, right? So I think.
There's also one thing that if G belongs to that place, G dot A. So why there should be any point A where small k belongs to capital versus G dot K? When the.
No, I'm just saying there is only finitely many things that if they fix a point, then there is only finitely many, that's all I'm saying. They may not. I'm saying. So,
But also here also analytical. You see that now Gx not belongs here for some G. So you said GH is contained in a finite set here.
so I was saying I have this finite group, which is fixing a point in K. So it
No,
has
but
to.
why does there exist a G such that Gx not belongs to K?
Why? Because my
The
action,
is transitive or something?
because the action is co-compact, so GK is all of
Or
X.
GK is.
Yeah. So,
Yes.
yeah,
No, yeah.
there's some details missing, but the goal to show this proof was to like really show you how we really use co-compact and proper discontinuous. Need both these things.
So you have finitely many conjugacy classes of every finite speech.
Yes. No, there are finitely many conjugacy classes of finite groups.
That's why.
After conjugation, there are only finitely many finite circles. It's not like you can have infinitely many conjugacy classes.
Yeah, every finite group, the number of conjugacy classes inside the big group G is finite.
Yes.
And these are
There's something wrong about the way you're saying it. I
Is
don't
it?
like it.
Oh, okay.
yeah. And these are not shown by the center point.
Yeah. So this was all to just like stress, and if you have a group acting geometrically on a Cat0 space, you can really get some algebraic information about that's the upshot. Okay. So I have 15 minutes and I do want to finish one definition. So I want to define something called an MK polyhedral complex. Very briefly, you should, if you remember simplicial complexes. So in simplicial complexes, you're gluing simplices together. Now what I want to do is I want to glue some polyhedra.
What is K? K could be any real.
Any of them. I want to glue some polyhedra, so I could be gluing Euclidean polygons together, Euclidean polyhedra together, or like hyperbolic polyhedra together, something like that. It's just a generalization of simple complexes. Okay. So for K and R, and MK polyhedral complex. Is a space X built out of from disjoint union of convex polyhedra in, let's call them PI, in model space of some dimension. Like I'm allowed to have different dimensions, right? I want 0-dimensional points, I want 1-dimensional polyhedra, 2-dimensional polyhedra, 3-dimensional. I'm allowed to have different dimensions by identifying along pieces, by isometry along pieces.
You have been different on that polyhedra problem.
Yes. Right, okay. I had actually, I rearranged things and I had to find it in my notes earlier, so I skipped it. Thank you. So what do I mean by convex polyhedra? Let's see.
Oh, yeah, okay.
Yeah, maybe I'll just say it, I want,
Like it's a polyhedron which is convex.
yes, that's all, yeah, so in Euclidean space, in Euclidean n space, a convex polyhedron is basically the intersection of finitely many half spaces. You take hyperplanes, codimension 1 hyperplanes, and then you choose a half space. So convex polyhedra is the intersection of finitely many codimension 1 spaces. Hyperplanes, yes.
We are just optic to describe. If I am to for
Because it's the spot,
Yeah.
it's distance, then I can.
we are taking medium.
So among the equidistant ones, you're taking the shortest.
Yeah, we are optimal distance.
Yeah,
If I
yeah,
take-
yeah, maybe that
Maybe
fixes
that
it.
will fix it.
So that's, she's suggesting a fix to your question.
Okay.
So it's not just like points which are equidistant from my set,
Yeah.
but they are the minimum, like the least distance. Be the minimum over those points, so then you will get the,
Then again, you get thing, you know, polyhedron.
no, because the ones in the North Pole and the South Pole will be.
No, there's one at that, whatever the minimal distance on that side.
So the one in the plane would be the shortest, because once you take a sphere, the North Pole is.
Having a Z coordinate. or-
No, I don't have to take the sphere.
Ah.
On that line, I can just take a point of the same distance. So whatever the minimal distance, you know.
No, but the distance would be along the hypotenuse.
Hypotenuse.
Beyond it.
That would be.
Have an extra Z component.
Yeah. Yeah, thank you.
I thought you would have always. Okay, so I think. So how is the identification done?
Identification is like if I was doing, let's say Euclidean,
So you're taking disjoint union of this like.
Yeah. Yeah, and then I glue them along isometrically along faces. So I'm not allowed to. I think I'm supposed to like glue full face to its full face. Yeah, I think I'm not allowed. I'm not allowed. Not allowed this, yeah. The two faces have to be isometric when I do this. Yeah, let me draw this example. Like, for instance, I could have three squares. Glued like this, it's just three squares. Yeah, that's an example of I would say this is an example of a M0 polyhedral complex. Next, now I want to know, the question is, when is this? The first thing is, when is this polyhedral complex? So when is X? Let's call it X. When is X geometric metric space? Right, if I want to, and the second question would be, when is it cat zero? When is it? Sorry, cat K.
So the joint is a convex polyhedra, you take, is a finite number of them or?
No, they can be infinite.
You could find this, when do they do the identification? Whenever you take two convex polyhedra, whenever one face of this is like the homomorphic, you always identify it.
No.
Or there is this specified kind of things which are identified or
Depending on your scenario, you might identify them, you might not.
you would.
I'm just saying it like if it satisfies this thing, that's called a polyhedral complex. It's literally like a simplicial complex. Like, yeah. Except instead of simplices, we are working with polyhedra. Right, so ultimately I want to know when if I give you a polyhedral complex, is it cat K or not? Like it's, but before that I need to know is it a geodesic matrix or not? Okay, about this. And when is this a geodesic? So it's a fact, the geodesic metric space. So X is a geodesic metric space, then it is built out of finitely many shapes. Then built out of finitely many economically polyhedra. So just to give you an intuition, why am I talking about this? Because I could do this space. So let's say I have 2 points and I have some edges between them. Okay, I'm putting some one-dimensional polyhedra. What's a one-dimensional polyhedron? Euclidean polyhedron is just an interval. So I put something of length 1. I put something of length 1/2. I length 1/3. And I keep putting things length 1 over n. Okay, so that's a valid polyhedral complex. But it's not even a metric space. Because what's the distance between these 2 points? I can find shorter and shorter things. So they're not the same, but the distance length is easy. So it's not even a metric space. That's why, so just to give you an intuition, why do I have this finitely many isometric types of polyhedra? It's called finitely many shapes. You don't want these, you don't want this kind of pattern behavior. And that's enough to give you even a complete metric space. And somehow saying that if this is true, then in fact you get a complete geodesic matrix. And then you can ask whether it's cat 0 or cat K or not. Okay,
So there seems to be a serious question that when X is a metric space.
then yeah, actually, yeah. Um. Yeah, I think even, yeah, see, basically, even for a my example was just saying that it's not even a metric space if you don't assume this. But in fact, once you assume this, you get more, you get complete geodesic metric space. And then the question is, when is this thing CAD-K? Because I want to, so like again, the ultimate goal is I want Coxeter group to act on some polyhedral complex, and I would want to prove that that thing is CAD0. So I need a criteria that I can apply to my space later. And the criteria is, so there are two theorems, and then I have to give you a definition, one more definition. Theorem one, so X be a MK polyhedral complex as, let me just say as above to mean it has this nice property. Theorem one is that X is locally CAD-K. You can only if it satisfies something called the link condition. So I have to tell you what that means. And theorem two is that X is CAD-K if and only if satisfies the link condition, so it has to be locally CAD-K. And B. So basically I'm rewriting, there was a theorem, I think in the last lecture I said, when is a space CAD-K, so it needs to be locally, no, the theorem was if a space is locally CAD-K, then it's CAD-K if you don't have these isometrically embedded circles of length less than 2dk, right? So I'm just restating that thing here. So it satisfies the link condition and does not contain isometrically embedded circles of length. Less than 2dk. This thing is called the Gertz condition. Okay. So I have to check if our space is CAD0, if our MK polyhedral complex is CAD-K, I have to check something called the link condition, which I will tell you, and this like no isometrically embedded circle. So this link condition is supposed to tell you that the space is locally CAD-K. Okay, so like if I'm like the rough idea is if I have this empty polyhedral complex, the polyhedra are already coming from the model space, right? If I take a point in my polyhedra, the interior of the polyhedra, it already has a neighborhood which is CAD-K. And basically at the vertices, at the vertices is where I'm gluing a bunch of stuff together. And I have to understand what's the geometry at the vertices. And this theorem is saying, but if you want to check if every point has a neighborhood which is CAD-K, it's enough to check at the vertices. So this link condition is something you have to check in the neighborhood of a vertex. And that's enough to say that it's locally CAD-K, that every point has a CAD-K neighborhood. And the rough idea is that in the interior of these polyhedra, you are already CAD-K. The point has a nice neighborhood. But at the vertices is where you are doing different things. So, I don't know if I should okay, let me see link condition. I might take 1 extra minute. What's a link of a vertex? So link. So let's just do link of a vertex in a polytope. And let's just do it in, of a convex polytope. Link of a vertex of convex polyhedra or polytope. I guess I'm using both words, polyhedra. And then, if I know what a link means for a polyhedra, then I'll tell you what it means when I glue a bunch of those together. Okay, so this is the link itself is a convex polytope. Okay, so this convex polyhedra could be living in, it could be in the N sphere, it could be in the Euclidean N space, or it could be hyperbolic N space. Or like we were thinking of model space, right? These are my model spaces. So I'm really thinking I have a polyhedron and looking at its vertex. And I want to know what is its link. So yeah, the link is it's itself a convex polytope, but in the n-1 sphere obtained by taking unit vectors. Okay, before I write the full thing, it's obtained by taking a neighborhood of that point. Basically, if you have your vertex, draw a little sphere around that point and see how it intersects your polytope. So the picture. Let me do it for this side. So let's say I have a polytope. So I'm drawing a spherical simplex. Okay, this is my convex polytope. This is a right. This is a S2 convex polytope, and this is my vertex V. I want to understand what's the link of this thing. So I should be thinking, informally, I should be thinking of taking a ball around that point and see how it intersects with my pink space. And the way it will intersect with my pink space will literally be this way, just that much, right? Just an arc. And that will be the link. If I, in general, even in the Euclidean case, the link of this point, I take a ball and the link is just this thing. So, but then I want to put a metric on this. So I'm going to define it this way. It's obtained by taking unit vectors u in the tangent space at V in, let's call these xn. Such that u is inward pointing. So here, what am I doing at this point? I have the tangent space to my sphere. And what are the unit vectors that are pointing inward? I want to look at all the unit vectors that are pointing inward, like towards my pink polytope. And I want to take all those unit vectors. And those unit vectors like literally correspond to this arc here, right? That's the link. And then what's the metric on the link? So it comes with a metric. So it's really, so if this was my one unit vector u1 and this was the unit vector u2, yeah, I'm in the link. And at this point in the tangent space, I have this unit vector u1, unit vector u2. What's the distance between these two unit vectors in that tangent plane? It corresponds to the angle between them, right? It's that angle. So this is by definition the distance between u1 and u2. Now, in the unit sphere, and this is angle. So here, what's the length of this arc? It's 5/2, in the picture that I've drawn. So the link comes with a metric and it's always the angle between those two. Yeah. And then if you have, so this was length of a vertex of a convex polyhedron. But if I have a bunch of them glued together, if I have a bunch of them glued together, the link is just the union of. So maybe I have some gluing also. The link is going to be. Just take a neighborhood around that point. And that's going to be.
Inside the polyhedra or inside the unit tangent sphere.
The link?
Yeah.
The link is, yeah, I'm drawing it on this thing, but it's, if I were to think of the metric, I should really be thinking in the tangent plane here.
So if you're talking about the unit, then the, like, when you exponentiate, it might go beyond the.
Right, so I should really be thinking in the tangent plane.
Then how are you doing them in different polyhedra, because they have different tangent planes? Like that object is not a manifold, so that you cannot talk about.
Yeah, so I'm going to combinatorially take the union of the links in each polyhedron.
I think I have to add some more. For example, the definition of a link of a convex polyhedra doesn't mention anything at all about this. Don't it talks about taking unit vectors, u is ex.
This inward pointing.
Yeah, inward pointing.
This inward pointing means I'm pointing like towards my convex polyhedra.
Towards what does towards mean?
Because the convex polyhedra is defined by these hyperplanes and then choosing a normal vector.
You're working in XN, right? And the TN of XN. XN is one of those model spaces.
It's not extending the whole space. Right?
Model spaces.
Yeah.
So if you like taking the tangent space or the model space or the extent.
Yes. Yeah, so when I was in the two sphere, the tangent space at this point is the R2 plane. And I should really be thinking of the link as a circle in that R2 plane. Yeah. But I'm cheating and drawing it on the.
Sure.
Because if I don't want to think about the metric, I just want to think of it topologically, then I can just like draw it as on the simplex, on the polyhedra itself. But for the metric, I really need to like do this business. I think I will finish this later. I think I shouldn't eat into the lunch time. I'll tell you what link condition means.
So this notion of inward pointing is defined by this.
Yeah.
Can you repeat your statement?
No, I think the concept, no, for example, if you read like that, you read the definition, it doesn't make any reference to this convex polyhedra. The only place where this notion of convex polyhedra appears is the definition of the link of the vector convex polyhedra. It is that statement, why is it inward point? Inward pointing is like this defined in terms of that particular concept.
Yes.
Right, because like, as I said, polyhedra is what? Is the intersection of finite number of pole spaces. So when you are talking about like this, a polyhedra, there is something called a inward pointing. So the inward pointing business is defined in terms of that particular time. Yeah.
Yeah, I'll quickly tell you, like after lunch, I'll quickly tell you, just say what link condition means, and then we'll talk about Coxeter groups. Thank you.
Near this seminar, so please try to hear, let others.
Then I will submit. Correct, or I was having some later some sort of
So Mohan's contact.
As the distance around the.
Yeah, they have it. Yeah. There was in the model space, not filled in the model space, I'm allowed to measure the distance by going cutting a line. Not in my plan, in the model space, I'm.
It will not be a.
हे सगळं येतं व्यवस्थित
Always be.
Yeah.
तुझ्या रूम मध्ये मी चार्जिंग लावतो बॅग घेऊन जातो iPad घेऊ
Generated by that.
Yeah, actually, no, it will not. That really,
तिला घ्यायला पाहिजे होतं पण ठीक आहे
then when you intersect, it will be.
We are not taking the inner portion.
एका तासात कुठे दिवायला
What's it?
If it's a tetrahedron, then you see a two-dimensional thing.
No.
You're supposed to take the neighborhood.
Classes
Three-dimensional.
of every finite group. So
Hey, I think I have known this.
this set is
this is finite. Yeah. This will be that. So we are he's taking that gx not in k.
yeah, but that was for a specific G, right?
Gx not in that k. No. So every g ultimately gx not will start and stop in k because of the co-compactness of that. G capital G of k is equal to x.
Yeah, but
For every g, you will have gx naught will belong to no.
for example, if you take identity and x naught is outside,
Yeah.
and the one who are between the corner one's invariant, that one keeps the middle one also as it is. That was that, so that G was specific. One G for each GX.
Have to intersect.
Yeah, so for a choice.
And you just get GH, G inverse.
Fixing, you have that contained in
Yeah.
a group,
Yeah.
a finite group, finite set,
Yeah,
it's got fixing.
But then what does that? The finite unit.
Link is also a polyhedron.
When you say the number of conjugation classes, no, if you have.
That doesn't say that I was done this from the beginning, right from the beginning. That,
You can ask for me.
yeah, maybe no, this is an important one.
You can just go, no.
We can.
So which is.
Hyperplanes.
Also, I want, okay.
Hyperplanes.
You can ask.
So if you are doing medium convex polygon, then hyperplanes here. But if you're doing this, then it's hyperplanes here, which I do not define. Maybe that also I should do next time. Yeah. I didn't say what hyperplanes are in spheres. Just saying, and saying there are finitely many. Yeah, I have like 5 buckets and any finite subgroup you give me will be conjugate to one of them. Is what I was trying to say.
I see.
There are finitely many conjugacy classes of finite subgroups. Yes.
Yes.
That's why I was not happy with something about what you were saying was not something.
It does not say that there are finite many.
See,
There are finite many finite subgroups. It does not say this.
no, it's finitely many conjugacy classes. Yeah.
There are finitely many buckets which are conjugate classes of one finite group, some group.
Any finite subgroup in your.
Yeah.
Yeah.
Now, what we thought was if we take a finite group which then as G varies, GH, G inverse, this set is finite. That is what.
That's what we thought.
Okay. But
That
H
is
was
not correct.
arbitrary.
Yeah.
H was arbitrary. Yeah, H was any, but I think what I didn't explain properly was maybe why F was one thing. F was not arbitrary.
So H is not fixed.
Yeah.
No, H was any finite subgroup
That is fixed.
and I can always conjugate it inside F.
That
And F is something,
follows from co-compact.
Yeah.
Proper.
Yeah, F had nothing to do with each.
Right.
Yeah,
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 yeah.
So the number of finite subgroups then finite.
No,
With your A
it's
is
an infinite
finite,
group, I can have infinitely.
your A, so A is the collection of group elements, right? For which the case G is some point of K. So you can find completely except like G is comes as a subset of A for every finite group G and A.
But I can have infinitely many Gs.
So, but set A is finite.
That's why I'm saying there's a finite set and every finite subgroup can be conjugated into this.
But not necessarily that the conjugacy class of that subgroup is finite.
That is
Yeah,
there.
yeah, the conjugacy class of the subgroup could be infinite.
Could be.
I'm not saying anything about its conjugacy.
But there is one G, so there are only finitely many buckets for the whole collection of finite subgroups in your G. For every finite subgroup H you pick,
Many conjugacy.
you can take a G, you just land up in one of those buckets.
In each conjugacy class, there could be infinity.
So GH inverse for G varying over G that will be infinite. But at least one of those G's will come to this one of those.
Right.
Now I also understand why I was thinking the wrong thing. I was thinking the wrong thing.
Second, like. There is finitely many.
Finitely many conjugacy classes of finite subgroups. That's first statement. G has finitely many conjugacy classes of finite subgroups.
G has finitely
So
many.
there are
Conjugacy
finitely
classes
many
of finite
finite subgroups such that every finite subgroup is conjugate to.
Oh, finitely many, okay.
Yeah. Also, you said that locally cascade thing, how does that resolve the tree? The tree thing,
Even I was getting, I think I very conveniently erased it without really. It's the same problem again. Where would that be locally? Say it's locally calculated.
Something is locally cascade and something is.
No
circles.
Then
it's
Yeah.
cascade, but why is the tree local? It's the same.
We have a tripod. I've had the same tripod. Yeah, that's what I thinking.
Vertex. You know, it looks the same as
The small tripod.
So we cannot just take smaller take smaller edges. It's smaller portion of the edge. We cannot take that kind of neighborhoods. Whenever I
We ran into the same problem. That's all. I thought the theorem will help me prove it, but it seems like.
But we
we
can
ran
do
into
the same computation. I think we can do.
We can do some
We
computation,
can
okay.
do that length. I mean, I think that length is what is the Gromov product of any two vertices in this hyperbolic space. You have the geodesic.
But we're not in a hyperbolic.
Yeah, that I know.
Yeah.
But this tripod, these basically are hyperbolic. These trees are all hyperbolic.
Yes.
That length that you're getting, the third length, that is the distance of this P
This geodesic
minus
from the other
Q
point, yeah.
and minus the 2 times the distance of this spot.
Hmm.
Or P plus Q minus the 2 of that. So from there maybe some computation that 2 of P plus
And
Q
that
will be
same
same.
computation will also work for globally. Right?
Globally also it
Ah.
will work. Yeah, that's what I was trying to. But globally you might go skip vertices like the triangle she was drawing, like you're going all the way from a tripod.
Yeah.
Those may be difficult, but for tripod, I think you can directly
Directly do it.
do the P plus Q minus the 2 times the distance from the other vertex to the center. That would give you the distance P, right? And this distance P is preserved, Q is preserved, so that is going to P plus Q. The other one is 2 times distance. I think that is. But not sure. Yeah, yeah, we will discuss. You start. Yeah, yes.
I mean,
I'm coming by the way.
Diwali. You would have to come to the doctor and now mathematics and rate, that is more straight from you.
We have that. This is so much, I was going so fast because I feel like I haven't covered even half of what I want to say.